you're able to see the screen, right?
Yeah, yeah.
Okay, okay, cool. So today what we will do, I'll take you through potential, electrostatic potential, and its related shell theorems, and then a lot of questions we will do today. So
Okay.
first is, suppose if I have a set of static charges. So these are my static charges, and somebody is holding them so that they don't run away. Otherwise, they will repel and run away. So someone is holding them so that they don't run away. Now, whenever you have this kind of static charges, of course, it creates what is called electric field. But I don't want to deal with electric field or force because they are vector quantities. So I want to define something different, a scalar quantity, which again is there because of the presence of static charges only. So I define a new term, what is called potential, which is a scalar. Why I'm defining a scalar quantity is because it is easier to deal with scalars. So it's possible to deal with force and field, which are vectors, but sometimes there
Yeah, the
is,
directions.
yeah, because it has
Yeah.
direction, so there is a complication. So I want to define something called potential, a scalar, which will also help me to solve certain kind of problems more easily than field or the force. So to define potential, I'm just putting the conditions initially. To define potential, what we call as electrostatic potential, there can be gravitational also. So electrostatic, to define potential, there must be some static charges somewhere, some static charges in the surrounding region. So that is first condition. Then second is, potential is defined at a point. It can change from point to point. So potential is defined at a point. Like field can change from point to point. So potential also can change from point to point. Then one more thing, potential itself is not absolute. What I mean by that is, you know, different people can say different values for potential at a given point. Suppose at this point there is person 1, he says the potential is 10 volt, and there is person 2, so I'll use a different color. So there is person 2 who says potential is 8 volt at same point. I mean, this is possible. So there need not be a unique value for potential. So potential itself is not absolute. However, potential difference is absolute. For example, suppose there is yet another point, and this person 1 says potential there is 6 volt, then person 2 must say the potential there is 4 volt. They must be consistent, because for person 1 the difference is 4 volt, and for person 2 also the difference should be 4.
Right.
Individual values may be different. It's just like, I'll give a fantastic example. Suppose you are standing here, and let's say that's the ground level, and there is a block of mass m just at rest at this level. So this is you, but I am standing in the basement in the car parking area, whose distance from the ground floor is h. This is me.
Mm.
Now you say the potential energy of block is zero. That is, you say, and I say potential energy of block is mgh, and both are correct in our own way. There is no uh, nothing called wrong here, because you are standing at the level of the block and saying it is at ground level.
Right. This is the frame of reference. Yeah.
Exactly. But suppose this block has been taken to a height h1 and now is here. Now you say the potential energy is mgh1, obviously, and I say the potential energy is mgh plus h1. And if you look carefully, the increase for you and the increase for me are identical. The difference is same.
Yeah. MGH.
Huh.
Yeah, MGH. Yeah.
mgh1. Yeah. So in the same way, here when we come to electrostatics, individual potential values may be different, but potential difference is very absolute. So now let's define potential first by taking some reference. Let's first define potential at a point, and for this we choose potential at infinity to be zero. Very far away from the charges, we take the potential to be zero. Now there is a special case where you cannot take potential at infinity as reference. You cannot take infinity as reference if charge itself is extending to infinity. This is the special case. If charge itself extends to infinity, then for some mathematical or technical reasons, you cannot choose infinity as the point. Generally, the rule is you should not choose such a point as reference where there is a huge charge.
Hmm.
Suppose if I have a charge q here and you are saying a point charge and you are saying I'll take this as reference, that point itself where the charge is located, you cannot take that as reference. You take some other point, maybe this as a reference, maybe infinity as reference also is fine.
Hmm.
And again, similarly, if charge itself is going to infinity, like a line charge, infinite line charge, so you can't take infinity as reference because this charge is going to infinity. So there is some charge at infinity, some very huge charge at infinity. So you can't take that as reference. So generally, the rule is you take that point as reference where there is no charge technically. That's our idea.
Right.
Okay, now I have these positive charges. So whenever there are positive charges, they create potential in the surrounding area. Why they create potential is because they create field. So wherever there is field, there could be some potential, and potential could be changing and so on. So the conditions are, to define potential, there must be some static charges. So I have them, and I must choose a point where I should define potential. So okay, let's try to define potential here for these charges. We have taken infinity as reference and potential there as zero. So what you should do, you should bring plus 1 coulomb slowly. That's the agreement among everybody in the world. So we'll bring plus 1 coulomb slowly from infinity to this point, and in that process, whatever work is being done by us, the external agent, that we call as potential. So for example, if I have done 10 joules work to bring this 1 coulomb charge slowly, very important point is slowly, without increasing kinetic energy. If I have done 10 joules of work to bring it here, then the potential here is 10 volt.
10 volt. Right.
Okay. And now suppose if I try to bring it further nearer to these static charges, obviously there are more repulsions as you try to bring it closer. So I need to do more
Hmm.
work. So maybe I've done 20 joules of work to bring it here. So this potential is now 20 volt if I continue to bring it like that. Because I'm bringing it closer to these positive charges, so repulsions are more kind of, so I need to do more work to bring them. So that's the idea. Now, let us look at this scenario in more detail. So I've got these positive charges. Let me draw the field lines also. Suppose this is the field lines from these charges, like that. And I already said potential here is 20 volt and potential here is some 10 volt. Now you see, everything will fall into place. If you go along a field line, if you go along a field line like this, you see the potential is reducing if you go along the field line. So the rule
Yeah.
is along field lines, potential reduces. That is one point. I'll call it one. The second point is more interesting. Suppose if I release a positive charge here, if I release it, if I allow it to freely move, then these static charges are going to repel this and it's going to run away. So what that means is if given a chance, the positive charge would like to run away all the way back to infinity. So positive charge likes to go from a point of high potential to a point of low potential.
Right.
So I will write here positive charges would like to go from high to low potential. And what about negative charge? If I put a negative charge here, it's getting attracted and it wants to go this
Exactly.
way.
Yeah, so it will come closer.
Yeah, so it will go from low to high if given a chance. So negative charges if given a chance, negative charges if left free, like to go from low to high potential, like to go from low to high potential. So that is regarding negative charge. Now, uh, what I am going to do is, suppose these static charges which I have taken them as positive, suppose I take them negative suddenly. I swap them, I reverse them from positive to negative. Now the question is this. Now will these statements which I have written, like along field lines potential should reduce, positive charge would like to go from high to low, negative charge would like to go from low to high, will these also reverse, uh, or do you think they will be the same? That's a very tricky question.
Mm. See, the direction of the field lines will definitely reverse.
Correct. Direction of field lines reverse.
Yeah,
And now let's explore all these statements one by one. So the field is now
right.
this way. Now let's go back to the fundamental definition of potential. It is work done by you to bring plus 1 coulomb only, whatever be the case, slowly from infinity. So work done by you to bring plus 1 coulomb slowly from infinity to given point. That is the potential at that point. So suppose I want to bring the plus 1 coulomb here. Now at infinity, of course, there was no force on it, but the moment I come to certain finite distance, suppose if the 1 coulomb is here, it's being attracted by negative charges. It wants to run away, run. It's very enthusiastic to meet the negative. It wants to accelerate and increase the speed. But then I have to bring it slowly always. That's the definition. That's the agreement among all people in the world to define potential. So it wants to just run and come closer to these negative charges. But then, so what I need to do, I need this is the positive 1 coulomb. It's being attracted by the negative charges. So I have to apply an equal and opposite force and let it come slowly like this. So my force
Right.
is this way and displacement is that way. So I kind of am doing negative work now, right? It's
Mm.
like we have a dog in the house and suppose somebody has come and it's ready to jump on them. What I do is, suppose I pull it backward. So I'm applying a force back, but I allow the dog to slowly approach them and sniff them. So kind of my force is back, but displacement of dog is forward. So I'm doing negative work on it and not allowing it to increase its kinetic energy, kind of. So it's the same thing here. So I do negative work. So suppose if I have done, uh, let us say, minus 10 joules work till here. So potential here is minus 10 volt. To bring it to this point, I would have done only minus 8 joules of work because the magnitude is less. I brought it by from infinity till here only, lesser displacement. So magnitude, if you take the magnitude, it will be 8, but it's negative work. To bring it till here slowly, I need to do more negative work. So here potential is minus 8 volt, let us say. Now you see how the field lines are. Again, along the field line, if you go along the field line, the potential is reducing. From minus
Mm.
8, it's coming to minus 10. Minus 10 is lesser than minus 8 because they're negative numbers. So my statement that along field line potential reduces still holds.
Yeah,
Okay,
right.
and let's look at this positive charge. Suppose if I release a positive charge here, it wants to go like this. It would like to go from a high potential to low potential, right?
Yeah.
Suppose I release it here, it would like to come here towards negative charge. So again, that statement also holds that positive charge, if given a chance here, would like to go from high to low, and negative would like to go from low to high. So all these statements are correct. All previous statements hold here also. So everything holds. Along field line
Okay.
potential, along field line potential reduces. Positive charge, when you leave it free, would like to go from high to low potential. Of course, you can take positive charge from low to high, but you have to do work. You kind of pull it like this. You can take from low to high also, no problem. But if left free, it would like to go from. So you see how we have written. Would like to go from high to low, or if left free, would like to negative charge would like to go from low to high. But you can do the other thing also. You can take a positive charge from low to high also, but you have to do work for that. and same holds for negative. But if you leave them, they would like to, positive likes to go from high to low, negative likes to go from low to high. Same holds even here. Positive likes to go from high to low, negative likes to go from low to high. In all
Right.
these, okay, in all these cases, we are taking potential at infinity zero. That's our reference kind of. Now, what that means is if somebody is not taking potential at infinity zero, suppose he says, no, 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 my potential at infinity is, for example, 6. That means he has added 6 here. Now he should add that 6 everywhere because the difference should not change.
Okay. Yeah.
Okay, like if you go back to our uh, this example, potential energy for you, it was 0 here and it is mgh here, but I changed the reference. I'm saying this mgh1. I add that mgh1 here also to get mgh plus h1. Okay,
Hmm. Yeah.
I add it everywhere so to make it uniform so the difference will not change. So same thing, if somebody says potential at infinity is 10, everywhere you add 10 to the values which you got by taking that as 0, and it will appropriately change. Now, from all this, what I want to tell you is potential difference is absolute for all fellows. Though potential is changing, potential difference is absolute for all fellows, and I would like to define that. So, potential difference between 2 points, potential difference between final and initial point. So, V final minus V initial is work done by external agent to take plus 1 coulomb slowly from initial to final.
Right.
Okay, that's very logical. For example, if you go here, suppose this is my initial point, this one, this is my final point, and I want to take plus 1 coulomb from initial to final slowly. So I have to do a 10 joule work. That will be the potential difference between these 2 points, 20 minus 10. So let me write this integral force exerted by the external agent, the person, dot dr, work done by him, f dot dr, from initial to final gives final minus initial. And he has to do that slowly so that the work he is doing is only used to counter the repulsions and not increase the kinetic energy.
Right.
Now, this word slowly is creating a lot of trouble. So let me see if I can remove that word from the picture. Let me remove this. I don't like the word slowly. How can I remove that? So what I do is, instead of writing work done by external agent, see what is external agent doing? He's countering the repulsions, electrostatic repulsions or attractions or whatever. So if there is some force already due to electrostatic charges, he is opposing that so that this charge should go slowly so that it doesn't go fast. That means he is applying the same force in magnitude as those attractions or repulsions, but in opposite direction. Now,
Right.
if he applies a greater force, the charge will accelerate definitely. But you
Hmm.
recognize one thing: if he applies greater force, his force may be now more, but electrostatic force is still the same.
Also.
So if I define it in terms of electrostatic force, the word slowly is not needed. It's like, suppose I have a block of mass m. There is a gravitational force mg. Instead of electrostatic, now I am talking about gravity, which is also a conservative force. And I want to take this block slowly to height h, and whatever work I do in that process gives increase in potential energy. So increase in potential energy is work done by external agent slowly. So if he does work slowly without increasing kinetic energy, then all the work he is doing is only going in increasing the potential energy. The
Yeah.
question now the question is how can he do work slowly? So he should apply mg only. If he applies anything more than mg, the block will accelerate. If he applies anything less than mg, the block will not move. So he'll apply mg only. Now the question comes, sir, if he applies mg, net force is zero, how will the block move? So my answer is, initially to begin with, he applied a slightly greater force than mg, only by an infinitesimal amount.
Hmm.
And once the block starts moving, it not even gained speed, it started moving. Let us say its velocity is 1 millimeter per million years. That means you got to wait million years for it to see move by 1 millimeter, which is as good as in our lifespan it's not moving, but it's moving
Yeah.
slowly. So once it gains that velocity, then I make the force equal to mg only. Initially I applied slightly more than mg to get it start moving, and once it starts moving with a very very small speed, I make the force mg. And from there on net force is zero, but it had some small velocity which is almost 1 millimeter per million years. So in zillion years it would come here. So the work done by me technically is the force I applied, which is mg. If you forget about that small little extra thing which is as good as peanuts, and
Hmm.
it went by h, so work done by me is mgh slowly, and that is increase in potential energy, right?
Right.
Now suppose I don't apply mg, but I apply 10 mg. Now the problem is that now it won't go slow to this height h.
It will
uh,
acquire a kinetic energy.
it acquires kinetic energy also. So right now the work done by me is of course 10 mgh, right? And in
Hmm.
this, only mgh was the increase in potential energy. 9 mgh is kinetic. I can prove how 9 mgh is kinetic. For example, you see the acceleration of the block is 9g up, net force by mass.
Yeah.
Initial velocity is 0, displacement is h, final velocity 2 into 9g into h, and half mv square from here I am multiplying by half m is 9 mgh, which is exactly increase in kinetic, you see.
Right.
So if you take it fast, you are also increasing potential, but you are also giving it a speed, so you are increasing kinetic. But look at the idea of gravity throughout this process. Gravitational force did not change. This is what I was saying. Electrostatic force, your force might have changed, but gravity is still mg.
Okay. Right.
So
Constant.
work,
Yeah.
so work done by gravity is minus mgh still. Negative of work done by gravity will give potential energy irrespective of whether you move fast or slow. That's exactly what I am saying. So negative of work done by electrostatic force is slowly not required. Change in potential is, instead of saying work done by external agent slowly, I would replace this with negative of work done by electrostatic force, because both are equal and opposite. So whatever work you do, electrostatic is doing the opposite work if you do it slowly. So negative of work done by electrostatic, to take it from initial to final, I don't care whether you take it slow or fast, it gives the answer.
Right.
Like here, work done by gravity, the conservative force is minus mgh, irrespective of what force you apply. As it goes to h, you apply 10 mgh also, by the time it reaches h, work done by gravity is minus mgh only. Negative of that gives you potential energy, which is what I'm saying, whether you take it fast or slow.
Hmm. Okay.
So negative of work done by
Hmm.
gravity, negative of work done by conservative, negative of work done by electrostatic in our case. Is it okay?
Got
this
it.
is this is making sense now?
Yeah. Yeah.
Okay, now work done by for electrostatic force is given by, this is the electrostatic force
Q
on
E dot
plus
dr.
1
I
coulomb.
guess.
It should be given by QE. Q is 1
Q. Yeah.
because we are taking
E
1
dot
coulomb.
dr.
Yes, so you get the very famous result, integral E dot dr from initial to final is V final minus V initial. This is a very important relation, so let me write it. Final potential minus initial potential is, take it from initial to final, put a minus sign, calculate work done by electric field, or calculate E dot dr. That gives you change in potential. Now the reverse of this, reverse formula, I cannot derive it. There are some very higher level theorems, but E is given by minus del V. Do you know del operator by any chance?
Oh, this is divergence, right? I
Ah,
think.
exactly, exactly. So it is I dou
Uh-huh.
by dou x plus
Yeah. Yeah.
plus k dou by dou z. See, the rule is, whenever there is a line integral, a path integral, we are going in certain path here, right, from initial to final. Whenever there is a line integral, an equation in line integral, you can reverse it. you can reverse that integral, you know, with a del operator. Either it may be just a del, depending on what it is, or it may be a uh, del dot, which is called divergence, or del cross, which is called curl. Anyway, there is also this thing. For example, del cross F, if it is zero, force is conservative.
Yeah, I've heard of that. Yeah, yeah.
Del cross E, if it is zero, electric field is conservative.
Field is conservative. Yeah.
Okay, this kind of field is created only by static charges. It cannot be created by a changing magnetic field because that field is non-conservative. The electric field created by a changing magnetic field is non-conservative. So if it is a changing electric field created by changing magnetic field, this won't be zero.
It's not equal to.
It will be some mu naught
Yeah.
J or something. This is actually uh, some kind of reverse Faraday law, I can say. But
Okay. Yeah.
we'll not get into all that. We'll not get into all that. We'll just stop it here. So the reverse is this: you can get electric field from potential by using the gradient. Okay, now let's look at this in more detail. V final minus V initial is minus integral E dot dr. There are many things here which we should explore. First thing, if E is 0 in certain region, then the integral vanishes. The integral vanishes.
VF is equal to VI.
So which implies potential difference is 0,
Yeah.
which implies potential is constant, may or may not be 0. Now that's very important. May or may not be 0. So in the region where field is 0, potential is constant. I can say that much. Is that constant 0? I don't know. May or may not be. That depends on the reference and many other things. For example, if you take a shell and it is uniformly charged, Q, radius R, we saw by shell theorems that field inside is 0 by integration and all that. Yeah, you can check
Right.
the
Yeah.
integration. So in this region, potential is constant. Wherever field is 0, their potential difference is 0, so potential is constant. In fact, this is not 0 here. If you take at infinity, it is 0. Here it will be on the surface, that will be kq by r actually.
Yeah.
Potential inside a shell is potential on its surface. How did you get kq by r? I'll talk about that in a few minutes. But all I want to say is if field is 0, potential in that region is constant. That constant may or may not be 0, depends on the given scenario. Then next thing, if you go perpendicular to field, your dr vector is always perpendicular to field, let us say. So let me write it on the next page. V final minus V initial is minus integral E dot dr. Suppose my dr is perpendicular to E always. That means at every moment I am going in such a way that my displacement vector is perpendicular to field. Suppose my field lines are like this, I am kind of going like this. This is my,
Right. So again, it becomes 0.
yes. So then this becomes 0. Again, potential difference is 0. So between any 2 points on this line, potential difference is 0. So this is a line of constant potential, or what we call as equipotential line,
Right.
or equipotential line. So what I'm trying to say, if you go perpendicular to field, potential will not change. Very important. If you go perpendicular to field, potential is constant. So lines perpendicular to E lines are called equipotential lines, are called equipotential lines. Similarly, you can have surfaces perpendicular to E are called equipotential surfaces, are called equipotential surfaces. For example, if I have a sheet of charge like this, something, it creates a field which is uniform and is like that. Any area perpendicular to this field, in fact, it will be parallel to sheet. This will be equipotential because it is perpendicular to field lines.
Right.
So you can have a series of equipotential surfaces. For example, this may be 10 volt,
बेटे मैं
this may
जान
be
पाते बंद करता
8 volt. You see, along the field line, potential should reduce. So I took the first one as 10, second one as 8 actually, like that. Because along field line, potential will reduce, right? So this yellow colored fellow is all at 10 potential, the shaded one. Uh, this is all at 8 volts potential. Okay, so these are some important things. Now let's get to let's take a point charge and let's try to find potential difference between 2 points, one which is at a distance r1 and two which is at a distance r2. Potential difference I'm finding, so there is no question of reference, it's absolute, it's same for all observers. If you talk about potential, that may depend on reference. So now I will, what I am doing, I am taking plus 1 coulomb slowly from, or you can take it fast also, no problem, because we'll use the other definition. So I take plus 1 coulomb from here to there. So V2 minus V1 is negative of E dot dr from 1 to 2. Negative of work done by electric field on 1 coulomb, conservative force, while taking the charge from point 1 to point 2. And we know the field due to point charge. So as you are going from 1 to 2, distance is changing. So you take some intermediate position where field is q by 4 pi epsilon naught r square r cap dot dr
हम्म
from r1 to r2. You take like this. So minus q by 4 pi epsilon naught comes out, integral. R dot dr will be dr only because both these are in same direction. So length of first vector,
हम्म
which is a unit vector 1 into length of dr into cos of 0. So it will be dr by r square ultimately from r1 to r2.
right
So I'll observe the minus sign because 1 by r square gives me minus 1 by r. That minus and this minus get cancelled. So I can
yeah
say,
so the art was oh,
yeah, q by 4 pi epsilon naught. So I'll write it as 1 by r from r1 to r2. So 1 by r square gives minus 1 by r, but that minus got nullified with q.
हाँ got it yeah got
You
it
know? So I can write it as q by 4 pi epsilon naught r2 minus q by 4 pi epsilon naught r1. This is nothing but vr2 potential at r2 minus v final minus v initial we wrote, right? V2 minus v1, that is potential at r2 minus potential at r1. This comes out to be q by 4 pi epsilon naught r2 minus q by 4 pi epsilon naught r1. That's the potential difference due to point charge. Is a absolute result, doesn't depend on any reference. This is true for
right
any observer having any reference, I don't care. Now let's come to our standard reference. For a point charge, we can take infinity as our reference because the charge is here and it is not extending to infinity. So we'll take infinity as reference and we'll take potential at infinity 0. So you can put any one of these r2 or r1 to infinity and potential there to 0. For example, I can put r2 tends to infinity and potential at r2, that is potential at infinity, I'll take it as 0. I'm now choosing a reference. So if you do that, I'll put r to infinity. So v infinity minus v r1 is q by 4 pi epsilon naught, q by 4 pi epsilon infinity, this will become 0, minus q by 4 pi epsilon naught r1. So from here I get v at r1 is v infinity plus q by 4 pi epsilon naught r1. Now you see here, this is the tricky part. This result is also absolute.
mm.
But now you
yeah
took v infinity 0 and hence you get q by kq by r. You took this as 0 and hence you got vr1 as kq by r1. If you took v infinity 10, you would get 10 plus kq by r1. This is what I was saying. If you add a particular value at one point, you must add that at every point.
yeah
So our formula of kq by r for potential has a restriction. This is valid only if potential at infinity is 0. That
t
should be,
zero yeah
this should be specified all this. This should be specified. Okay, now generally we don't change this reference unless the charge itself is extending to infinity. If it is line charge, we cannot do this. We cannot take infinity as 0. We cannot take reference at infinity at all. First, forget it. Forget taking it as 0, but you cannot even choose that as reference. Wherever there is charge present, you can't choose that as reference. Choose a point where there
mm.
is no charge as reference. That's the rule. Because
right
because if charge is there, the problem is there, the force is infinite, and you are doing this business of bringing 1 coulomb from there to here and all that. So if force
Hmm.
is infinite, the work done and all will blow up. So
Yeah, that it won't be valid in this that
it
case. Yeah.
won't. Yeah, it won't be valid. So that's the idea. Okay, now with this background, now let's look at shell theorem. So if I have a shell, again, charge, it is uniformly charged on the surface. So for outside points, for example, here at P1, by integration, I can show that it is as if charge is at center. So if it is a point charge, we already found potential it is kq by r1, but of course, v infinity we have taken as 0. So for outside points, shell behaves as point charge at center and you get same potential as point charge. Inside point, as I told you, if you take P2, potential at P2 is potential on surface because potential inside everywhere is constant.
Yeah.
And to get on surface, keep charge at center, so you get kq by r.
Take away R.
So I'll take this as r, so that kq by r. So this holds for shell or even conducting sphere, conducting solid sphere. Because even in a conducting solid sphere, charge comes to outside, even if you give it inside. We argued with Gauss law that field should be zero, charge inside must be zero, and all that, right? So it comes to outside. Now we are left with non-conducting solid sphere. This result is very important. Very important. This is the toughest result. Non-conducting solid sphere, uniform charge, uniform charge. So I've got a non-conducting sphere, solid. Now wherever you give the charge, it is there, but I have charged it in a uniform way. Let us say something in a uniform way. Okay, I'll keep it like that. Let us say the total charge is q, radius is r. Outside point, no change. If you take a point P1 at distance R1, potential there is potential at
KQ
P1
by
is,
R.
yeah,
Yeah.
kq by R1. We take infinity as our reference. Now inside point at a distance R2. Now this result is very strange. So potential at R2 is potential on surface into 3r square minus r2 square by 2r square. How the hell did we get this? How did we get this? There are many ways, I mean, two ways at least to derive it. I'll derive in one way. So, what you do, this is a non conducting sphere, right? So, the radius is r, there is charge everywhere inside. So, you go from this point, which is at a distance r to 2, to a point P on the surface. You go from here to there. So you have Vp minus V2 is minus integral electric field dot dr from R2 to R, right?
Yeah.
So you took 1 coulomb slowly from here to there. Your final position is P, initial is R2. So final minus initial is minus integral initial to final E dot dr. And we know E inside is Q R2, I mean at a distance R, QR by 4 pi epsilon naught R cube
R
dr,
cube. Yeah.
dr. Yeah. So this actually I should write r dot dr, but these two are in same direction, so I can just remove the dot and even arrows.
Hmm.
Okay, magnitude of r into magnitude of dr into cos 0. Cos 0 is 1, so I wrote it like that. So now we know Vp on the surface. Again, you can keep charge at center and calculate. So Vp is, q by 4 pi epsilon naught capital R. I want V2, so I have minus q by 4 pi epsilon naught R cube. You get r square by 2. So r square minus r2 square by 2, right? You get this.
Yeah.
So I'll take v2 that side and bring this from this side. So v2 is q by 4 pi epsilon naught r plus q by 4 pi epsilon naught r cube into r square minus r2 square by 2. What I'll do is I'll take q by 4 pi epsilon naught r common. You are left with 1 plus r square minus r2 square by 2r square. So q by 4 pi
Yeah.
epsilon naught r, take LCM, 3r square minus r2
Minus
square
R square. Yeah. Yeah. Got it.
by 2r square. This is exactly this
Yeah.
potential on surface, and you are multiplying that with this factor. And if you put R2 equal to R, you get 1, so that you get potential on surface only, right? You should get that. When
Hmm.
R2 is R, on the point is on the surface, you should get potential on surface. So this result, very important. We have to remember it, no choice, because we can't derive it in exam. You can technically, but better to
Very
remember.
time consuming. Yeah.
Yeah, so better to remember it. So this is as far as the uh, shell theorems are concerned. Now, if I put all shell theorems on one page, let me write it. Shell theorems, before I go further to more complex questions, shell theorems at a glance, both for field and potential. So if I have shell or solid conducting sphere, both results same, solid conducting sphere. So I gave a uniform charge. All our shell theorems are valid only for uniform charge. Radius r. I take a point P1 at a distance R1. I take a point P2 at a distance R2. So field at P1 is KQ by R1 square. I can put R1 cap. Field at P2 is 0. Potential at P1 is K. Sorry, my bad. No arrow. Potential at P1 is KQ by R1. Potential at P2 is potential on surface, that is KQ by R. This holds for shell or even solid conducting sphere. Now, solid non-conducting sphere, which is in itself a special case, solid non-conducting sphere. So we have got charge everywhere. Wherever you put charge, it is there, it is not moving. Q, radius R. Outside point again, same as shell. Field at
Hmm.
P1 is KQ by R1 square R1 cap. Potential at P1 is KQ by R1. Now, if you take inside point R2, P2, field at P2 is
Take
KQR2 by R cube. That result
R
you should
cube.
know.
Yeah.
Yeah. And the most toughest thing is potential at R2 is KQ by R,
R 3R square minus R square by 2. Something like
R
that.
square.
Yeah.
Yeah. Yeah. This one.
Yeah.
So this is shell theorems all at one point. Now let's go to some very interesting, beautiful set of questions. First question.
Right.
I'll give a chance for you to try. Just give a try. Let me just suppose I have three three shells. This has radius A, this has radius B, and this has radius C. This is given charge Q1, this is given charge Q2, this is given charge Q3. Here is a point P1 whose distance from center is R1. Here is a point P2 whose distance from center is R2. And here is a point P3 whose distance from center is R3. Uh, and there is a point at a distance R0 inside the inner shell also. I am unable to show it. Actually, what I need to do, okay, I'll just say there is a point P0 inside,
Inside the smallest shell. Got it.
yeah, innermost shell at distance R0 from center. So our task is, we take potential at infinity as 0. Our task is find potential at R0, find potential at, P0, find potential at P1, find potential at P2, find potential at P3. So You have to apply shell theorems for each shell and then try to get this. Just give it a try.
Right. These are non-conducting, like normal, right? Just normal shells.
Yeah, normal shell. Even if it is a conducting, for a shell, because that thickness is negligible, you can say the charge, whether it is on inner or outer surface, doesn't matter. The distance is same only. For example,
Right.
so for a shell. But you are right. If I take a thick shell, I must mention whether it is conducting or non-conducting. In this case, I'll say non-conducting cells. Three shells, non-conducting. Better now.
Okay, so for R naught, it will be the same for like all the three shells at the surface. So like KQ by A plus KQ2 by B plus KQ3 by C.
Correct.
Then for R1, it will be KQ1 by R1 plus KQ2 by B
Correct.
plus KQ3 by C.
Correct. So you got it.
And
You nailed it.
yeah,
That's it. So this way you do it.
yeah.
Absolutely. Now let's look at something very interesting. Now suppose I have a solid metal ball uncharged, and here I brought a charge q, and this has got a radius r, and here is a point p, and this distance is given to be r1, and the distance to the center is given to be d, and let's say this angle is theta. Now question is, find net potential at p. Potential at infinity is taken to be 0. So this is the question. Now think about this. Now first thing is, it's a solid metal ball, so even though it is uncharged, the moment this charge is put here, its electric field tries to penetrate through this sphere. It's going to pull electrons like this and push positive charge like that. Because it is as a whole neutral, if this is minus q, that's going to be plus q. Now the question is this. Now there's not just this charge. There are also these charges. So we got to find the net potential at p, which means due to all the charges. So that's the question actually.
Mm.
So you think about that, how you will find it. ఆద్య డిస్టర్బ్ చేయక అక్కని ప్లీజ్ వద్దు అక్కడ కూర్చో
Mm.
నో
You can't get think of anything.
okay I'll give you some intro. This is actually a classic problem. I'll tell you why it is classic, because this concept we'll use again and again in such kind of problems. Suppose there is some induction, there is some minus and some plus here. Suppose this is some minus q and that's some plus q. I don't even know what are the values of this minus q and plus q. It's like, if you take this q very far away to infinity, then there is no induction and minus q plus q will be zero values. As you
Yeah.
start bringing this charge q, there will be more and more induction and so on. So anyway, now I want potential at p due to just a capital Q. I can say kq by r1, right? Because
Yeah.
that distance is given to me.
Yeah.
The whole problem is these bloody charges. These distances are so weird. We can't even guess. Like these distances are. How do you calculate potential due to all these fellows there? The answer is you can't calculate potential of these fellows at P directly. So direct way
Mm.
will not work. We are in trouble. Direct way will not work.
Right.
Now you see the indirect way. This is what is electrostatics actually all about. This whole region is a region with zero field, right? Because it is the medium
Yeah.
metal. That
Correct.
that means their potential is constant everywhere. It is not changing.
Mm.
So I will find potential at center, and that should be equal to potential at P.
Okay. Yeah.
I mean, why center? Because center has got a great advantage. It is equidistant from all these fellows. At least
Yeah. Correct.
So now potential at center due to outside q is kq by d, right? And due to all the surface will be zero because ultimately those charges are adding up to zero. It's like if you call these charges as q1, q2, q3, and q5 and
Yeah, I got it. I got it. I got it. Yeah.
right. So kq1 by r, kq2 by r, kq3, and sum of all these q. So ultimately I got it directly in one step as kq by d. You see. And potential at c I got it. That should be potential at p. I mean, this R1 is not coming into the picture, but that's the way it is. This is this B. So the answer is KQ by D. Surprisingly.
Oh, sure.
So we must recognize, whenever there is a region of zero field, very important for us because there the potential is going to remain same. So that's a very important idea. So uh, where I would just put that here, where field is zero, those regions need extra attention because potential is constant. And somewhere in that region there may be a point which is very symmetric from the charges. So that's the idea. Now let's go to earthing. There are problems where there is earthing happening, and all the concepts we have learned till now, like the distribution of charges, Gauss law, conservation of charge on isolated system, electric field made of metal, zero potential, earthing, everything can be clubbed and given problems. I mean that is my ultimate aim. I want you to take there. So
Hmm.
let me talk about
Hmm.
earthing. First of all, earth is fantastic conductor. Fantastic conductor. It's a huge conductor. It's a huge conductor. I mean, if you have any doubt about it, think about this. All metals are dug from earth.
Okay. Yeah.
Everything that you got, your gold and silver and steel and iron and whatnot, every aluminium, everything is there in the earth. So earth is a fantastic conductor, and I can say it's a huge source of positive and negative charges. Technically, for my purpose, I would take that as infinite positive and infinite negative charge.
Infinite negative. Right.
Okay, so it's like if I took a bunch of electrons from Earth, Earth will say, you did not give me any charge because I am Ambani. It's like you took 100 rupees from Mukesh Ambani and then you go to return to
Yeah.
him. He will say, hey, keep it with you. I'll give another 10 lakhs. It won't affect my money at all. so,
Right.
so Earth is like that. So it's got infinite amount of positive and negative. So after taking also it is still there. So nothing changes. So and it is neutral. It is neutral conductor. So as a whole, it is neutral. It doesn't have any charges together because total positive and negative is both are infinity. Total is zero. So I can
Right.
say
So,
potential of Earth
to zero.
equal to zero. Potential of Earth is zero because it's like it's a huge ball, but then no charge. Uh, so there is no charge, and you can say potential is so. Uh, Generally, what do we say? If there was a charge, kq by r is the potential, but there is no charge, so potential is zero.
Right.
But again, keep this in mind. This we are taking this because potential at infinity is also zero in a sense because kq by r is applicable only for that condition, right?
Yeah.
If you took potential at infinity as some 10, I would also say potential at earth is 10 in that way, even though there is no charge. Maybe there is something else somewhere, I don't know. So anyway, right now we choose our reference at infinity. Potential at infinity is zero, and we say potential of earth is zero.
Yeah.
And any object, any metallic, particularly any metallic object connected to earth by wire, connected to earth by wire, reaches same zero potential. Let me tell you how. See, suppose I have got a sphere which is positively charged. Okay, it's got some potential kq by r on the surface, and suppose I
Right.
connect it with a switch to earth. So this is the symbol for earthing. I connect it to earth. Then what happens is right now the potential of this whole sphere is kq by r. It is high and earth is zero, and charges, if given a chance, positive charge would like to go from high to low potential, so they would move.
Yeah.
So what happens is, after connecting, all this charge went to earth, and the sphere says, hey, you see, I gave you some money, that is charge. Earth says, hey, I am Ambani. You did not give me anything. I already have millions of money. So all the charge disappeared. Technically now earth has zero charge, sphere also has zero charge, and the
Right.
sphere reached the potential of earth, kind of. So potential zero.
Hmm.
Or even if you have a negative charge, it's like uh, negative charge, and you give to earth, this all vanishes. It reaches earth.
It'll all, yeah, it'll all go back to the earth,
Go
right?
back to the earth. There is some other case which I want to tell you. Suppose I have got a metal sphere, a very interesting case, in fact. Suppose I have got a metal sphere, okay, and I brought a charged rod near it. There will be induction. So this is a rod which
Hmm.
is charged. So there will be induction minus and plus. And after this, suppose I have a switch and I earth it now. I connect it to the earth. What happens is, this positive, there will be negative. I don't know the arrangement, it is very complicated. But the negative is not going to earth. The answer is, these negative are must be there to make potential zero. Because if this negative is not there, then there will be some potential here, kq by r.
Or to the rod, right?
But whatever is earth should not have potential. So the negative will stay here, only positive would have gone to earth. And earth is saying, boss, I know you are creating positive potential, so I'll let negative charges be here and create a negative potential, and together it will be zero.
Oh, right.
Okay, so that's the idea. So which means that I can create a problem around this. You see, suppose I have q, I have a metal ball. I say this distance is to the center d, this radius is r, okay, and I have a switch. So this is a metal ball. So after switch is on, okay, find the charge induced on surface of sphere. So after the switch is on, after I put it on, what will be the final charge that will be present on the surface of the sphere, metal ball?
So is the ball charged or
No, no,
uncharged?
ball, metal ball initially uncharged. Initially uncharged.
Uncharged.
Yes, initially uncharged.
Mhm.
Uh, Due to induction, there may be some separation of charges. I am not denying that. Then you connected it to earth, and something might have gone to earth. Something remains on the ball. So I
Right.
want finally what is remaining on the ball.
If negative charge goes to the ball, isn't the potential already becoming zero?
Uh, I mean, if you say there is no charge on the ball, then there will be some potential due to this capital outside capital Q.
Yeah.
So potential is not zero, but other thing should have potential zero now.
Hmm.
Assume this is a
Uh,
positive charge. For example, let's assume this is positive. This is exactly the. Can you see the rod case here? There is something
yeah.
remaining. Instead of rod, I kept a point charge here. That's the only difference.
Hmm. Uh, so if what if like because the charge Q there'll be equal amount of positive and negative charge that gets generated on the
And we don't know the magnitude of that. That is something which we cannot guess, at least, right?
yeah.
So ultimately, let's look at it like this. Ultimately, when you earth it, that positive would have gone to earth, and that negative remains here in some form.
Yeah.
So I'll call it minus q, and I am trying to find that magnitude only right now, right?
Hmm.
Now, I'm saying this whole is equipotential, so potential should be zero.
Right.
because it is earth. Any earthed object should have potential 0.
0 point. Yeah,
Uh,
correct.
and inside field is also not there. So this whole, all these points are at same potential and it should be 0. I'll rather take this point which is very convenient for me, and I'll say potential there is 0. So kq by d plus k minus q, and equidistant points r should be 0. So q should be qr by d, right? So the negative charge is minus qr by d.
Oh, right. Got it. Yeah.
So this is kind of, I'm combining this idea, whatever we did here, the classic idea, with earthing now.
Hmm.
Here also the idea was it is all
Oh, okay.
equipotential, but now I am going an extra step and saying this is also zero potential. Not only equipotential, this is all at zero potential because that it's
It's
at,
0. Right.
okay.
Right. Got it.
Now, if these charges are not there, it couldn't have been zero because Q creates some potential. So together, this Q and that negative charge is
Hmm.
creating zero potential.
Right. Okay. Got it.
And you see, I'll tell you something very strange. This induced charge Q, small q, depends on distance d. You see, suppose I make d
Hmm.
infinity, this charge is very far, then there is no induction.
Yeah, it'll be 0.
Okay, that makes sense. So as you bring it closer, the induction is more, and so the value of small q depends really on the distance d.
Right. Yeah.
So that is one important thing. Now let's look at questions where you have. I just want to take one last question and tell you something here. Suppose uh, I'm almost coming to the end of my whole discussion. Suppose I have a charge, a metal shell A. So these are metallic, let us say
Okay.
metallic. Suppose I gave a charge Q1 here, I gave a charge Q2 here. Now what I am doing, case A, I am earthing outer shell. Case B, I am earthing inner shell. So the question is, after earthing, find charges on inner and outer surface of each shell. So
Mm,
let me help you do this problem because this is a bit tricky. Because in this problem, every bloody concept which we have done till now has been included. It looks
right. Yeah.
so simple, but I am earthing. There is some potential related stuff. I'm also asking charge on inner and outer surface. So there is a charge distribution, Gauss law, charge on isolated system is conserved, shell theorems, everything. Every bloody damn thing is there here. So we have to do this very slowly. So first, what I do, I take the case of, this is case one. I take the case of outer shell being earthed. Okay, outer shell being earthed. So let's first do that. Oops. So this is my inner shell. This is my outer shell, and outer shell is earthed. Initially, inner shell had Q1 and outer shell
Right.
had Q2, right? And then this is
Q.
radius A, this is radius B. Now, when you earth outer shell, what will be the charge on outer shell? Many people think that this will go to earth. No, no.
No.
The
The
concept,
potential is 0. Oh,
potential is zero. So the correct concept is, the correct concept is this. For example, here after earthing, earth gave kind of negative charge to this ball, right? You see a negative charge on it. So earth gives appropriate charge to bring potential to zero. Earth's job is only one thing. Earth gives earth gives appropriate charge to make potential zero. That's the whole concept. Let's go back and see whether this concept is correct or not. Okay, let me start with uh, earthing this. So here, when you connected this ball to earth, earth gave positive charge to nullify this negative and made total charge zero and potential is zero, right?
yeah.
Earth gave a positive charge
Yeah.
to nullify this, so that ultimately there is no charge on this and potential is zero. Here,
Yeah. Got it.
here Earth gave a negative charge See, actually, if Earth doesn't give anything, then what happens is all these will create zero potential, right? But this damn rod is creating non-zero potential. So total potential here is non-zero,
Hmm.
and this is all equipotential. So potential is non-zero, and Earth doesn't like it. So after connecting,
Right.
Earth gives negative charge and nullifies these fellows, and says to those negative charges, "Hey,
Right. Got.
you arrange in such a way that potential here is zero and also everywhere is zero." Now potential here is zero. Why? Negative charges create negative potential, but the rod creates some positive potential, and these negative have arranged in such a way that potential is zero, and they are happy. I brought the shell or the sphere to zero potential. So the rule is always this: Earth always gives appropriate charge to make potential zero. Now here also, when you Earth outer shell, it gave a charge y, let us say, which we don't know what
Hmm.
it will, to bring the potential to zero. Can I call
Okay.
q2 plus y as a whole as some x to make it simpler?
Right.
Nothing now. So I'll say whatever is earthed, whatever is earthed, give a fresh charge x to it. Forget whatever it has. Give it a fresh x.
Hmm.
Somebody will challenge, sir, why did you forget that q2 and gave fresh x? So my answer is I did not forget q2, but earth gave y. Together I am calling it x. Matter seed.
Right.
So now I must take a point on this and equate potential to zero, because after all, Earth gave charge to make bring potential to zero. So you will use shell theorems. Potential there due to Q1 is KQ1 by B, plus potential due to X is KX by B zero. So X will
Zero
be minus Q1, right?
minus Q1. Yeah.
So the total charge on outer shell is minus Q1. So now we have got charge. So this is A, this is the earthed fellow, this is B. Now total charge on this is minus Q1. Total charge on inner was Q1. Now, how do you arrange it? You take some thickness for these shells and apply Gauss and argue. This is 0, this is Q1, this is minus Q1, this is
Minus
plus Q1.
Q1. Yeah.
And outer will be 0 because total has to be Q1 minus Q1 for this, right?
Huh. Correct.
Because Earth gave. So this is how you arrange. So you have got your earthing, you have got your induction, you have got your idea of distributing charges using Gauss law. This is an isolated system, the inner shell, on which the charge never changed, right?
Yeah.
So it was the outer shell is not isolated because it was connected to Earth. So something came from Earth, it is not isolated. So its charge changed. It was having Q2
Right.
originally, but now it is Q1.
Okay. I got it.
So now let's do the same thing for this inner fellow. Now inner shell is that. So outer shell has Q1, this has Q2, this is radius A, this is radius B. Now inner fellow is Earth. Let us forget the inner charge Q2 and give a fresh X. Now,
Right.
somebody challenges you, say, boss, Q2 was there, Earth gave Y, Q2 plus Y, I am calling it as X. So there is no further argument from them. Now, whatever is Earth should have zero potential. So let's equate the potential to zero. So Kx by A,
Kx by A plus KQ1 by B.
B, because it is inner point. So
Yeah.
from here you get minus Q1 A by B as X. So you got the charge. So let's distribute the charge now. Uh, so inner surface 0, outer charge surface minus Q1
Minus
A by B.
Q1 by B.
Then here plus Q1 A by B, right? Because all equivalent of,
Yeah.
and but total is Q1. So outside will be Q1 minus Q1 A by
Minus
B.
Q1 A by B. Yeah.
Matters. So this is how you
Sure.
do earthing and potential kind of problems here.
Right.
So
Got it.
I gave everything in potential field. There are still some top class questions. Maybe you try them from some good books. Which book are you using actually for problems? I suggest you use Galaxy is a good book. It's got a lot of subjective and objective questions. DC Pandey is okay.
Huh.
It's okay, nothing, not bad. You can use it, but there are very tough questions in Galaxy.
Galaxy. Okay.
Galaxy
I
is
don't have I don't have like books many of them right now because we get sent material by the teachers.
you do material. You will have some graded material. Fourth level or something should do.
Acha. Okay.
You have got some 1 2 3 levels. I don't know what is there in that Narayana material, but it is
Huh.
too much voluminous. So what I suggest you do the toughest things only. Don't do the
Yeah.
easy
Yeah.
one. So go
Yeah.
for
Exercise 3 and 4. I will do 3 and 4 anyway.
3 and 4 you do and collect all the
Yeah.
tough questions. If you're not getting, we'll sit and blast all of them one shot.
Right. Okay.
So that will be done. So my trail for this chapter ends here. So I don't know. I hope I was useful to you. Whatever you
Yeah,
asked.
definitely. Thank you, sir.
So okay,
Yeah.
I'll send you this video. This video I'll send.
All